Upon completion of this lesson, students should be able to compare and contrast IT and OT, identify the implication of merging IT and OT to security, compare and contrast open loop and closed loop systems, list the main functions and components of open loop and closed loop systems, describe a process control system, PCS, and list the different modes of PCS operation. With an ever-increasing demand for immediate access to operational information for just-in-time decision-making, operational technology systems are becoming more integrated in the corporate information technology network. This complexity of integrating information technology, IT, with operational technology, OT, is becoming a critical issue in the information security landscape. An information, IT, system consists of the computing, networking, and software components that facilitate the processing of information to support the business objectives of an enterprise. Operational technology, IT system, pertains to the computing, control, and communication devices and software that are used to monitor and control processes and information in an industrial or manufacturing environment. One can view the IT system as a support for the business activities of the enterprise, while the OT system provides support for the operating processes. Traditionally, IT and OT systems are completely segregated. The newly found convenience of connectivity and the demand by stakeholders for immediate access to field or operating information has brought about the combining of information technology systems with operational technology systems. While this scheme presents some advantages, it enables security issues that can have a major impact on the OT systems. On purpose, the principal purpose of IT is to provide for the information processing requirements for the enterprise. These nuggets of information are critical to the decision-making and the management of business operations. On the other hand, the primary purpose of the OT system is to provide for the effective and efficient monitoring and control of manufacturing and/or industrial processes and equipment. In essence, OT is responsible for the product to be delivered by the business enterprise that is supported by IT. On architecture, while an IT system consists of all of the enterprise-wide computing and communication systems to support the entire business operation, such as those involving human resources, procurement, accounting, and sales. An OT system is built around embedded systems, sensors, and other equipment that comprise an industrial automation system. On interfaces, an IT system typically provides graphical user interfaces, GUI, and web browsers to facilitate business operations and transactions. An OT system enables the effective monitoring and control of processes and floor operations through human-machine interfaces, HMI, and electromechanical controls. Much of the physical interfacing activities are enabled through sensors and actuators, which in turn trigger the control systems. An example of this is the level sensor of a chemical tank that sends information to the controllers to start or stop the chemical pumps. On data repository, information within the enterprise is typically managed by the IT's database system. In the OT system, data and logging information are usually stored in the historian. The historian is similar to a database in the IT system. However, due to the control system requirement for real-time operations, the historian provides a much faster read-write capability than a typical database. Another feature that is found on historians but not on database systems is the more powerful compression capability. This feature is necessary due to the huge amount of volume that is stored in it. Just imagine the amount of data collected when the historian is set to collect the information in several sensors every 10 seconds, every hour of every day for several years. On ownership, the ownership of an IT system belongs to the enterprise. However, one may think of ownership as the entity managing the system. In this regard, ownership of the IT system is the IT system manager and the staff, which will include the database system administrator, the network administrator, and technicians, the system programmers, and application developers. On an OT system, the real owner is the utility company or the operator of the manufacturing or industrial company. Again, looking at the aspect of managing the OT system, the ownership really belongs to the operators, the engineers, and the system managers. On processing requirement, most IT system activities require non-real-time processing. Emails and file transfers are typical application examples that are not urgent and can wait. Corporate video conferencing is an activity that may require an enhanced quality of service, but is not as critical as those found in OT systems. The real-time processing requirement that is imposed on OT systems is due to the criticality of the operation. On connectivity, the typical IT system connectivity is enabled by the de facto network standard, Transmission Control Protocol, Internet Protocol, TCP/IP. On the OT system, there exists a plethora of proprietary and non-proprietary protocols that enable the connectivity of devices, controllers, sensors, actuators, and equipment. These protocols include, among others, Modbus, Ethernet IP, Fieldbus, Distributed Network Protocol 3, DNP3, Common Industrial Protocol, CIP, and Modbus TCP. On role, the principal role of an IT system is to support the people running the business operations of an enterprise. The OT system provides support for the controllers that enable process automation. In this section, we will look into the details of open loop and closed loop systems. Industrial control systems are classified by the way they control process variables such as flow rates, fluid levels, temperatures, pressures, motor speeds, material properties, and robotic maneuvers. The classification can either be open loop for manual control or closed loop for automated control. The open loop system is the simplest control system. The feed-forward process continues until a steady state, balanced condition is reached. The control is usually manual and with little or no provision on handling external disturbances, which can eventually lead to an unstable condition. The figure below depicts an open production mixing system. An operator periodically checks the quality of the mixture on the output. The system will initially be in steady state condition, but some external disturbance may have been introduced that affected the output. The operator recognizes this problem and manually adjusts either or both the input controls. The closed-loop systems are feedback control systems that monitor the output and send back information to the input to obtain the desired output. We present the same product mixing system as that in the open-loop system. The major differences are the two feedback lines that automatically send signals to the controllers. This closed-loop system is shown in the figure below. The sensor on the output monitors the mixture composition and sends a signal to either or both controllers on the input to make the necessary adjustments in order to get the desired mixture property. The main functions of a closed-loop system are reduce error by automatically adjusting the system output, improve the stability of a system, automatically adjust the system sensitivity, enhance robustness against external disturbances, and produce a reliable and repeatable performance. The following are the principal components of loop systems. Process variable. This is the variable that is maintained and controlled in the manufacturing or industrial process. Measured variable. This is the controlled variable at the point when it is actually measured. Manipulated variable. A variable that can be changed by an actuator or controller based on certain parameters. For example, in the product mixture above, the input mixture property is the manipulated variable, and the flow rates of input 1 and input 2 are the controlled variables. Measurement device. The device that performs the measurement of the controlled variable and communicates it to a controller. This device can be a simple thermocouple or a sophisticated sensor. Feedback signal. This is the output of the measurement device. Controller. This device receives the feedback signal from the measurement device and performs a control function to manipulate the controlled variable. The control implementation may be performed by a PLC. Actuator. This is the device that performs the actual manipulation of the controlled variables. For example, the actual control of the amount of input 1 and input 2 in the mixer system is put into effect by the gradual opening and closing of the intake valves, actuators. Disturbance. This can be a physical or logical factor that affects the stability of the control system. It can be a sudden change in pressure, a malfunctioning sensor, a failing actuator, or a non-standard process material. In this section, we will look into the details of process control systems, or PCS. Process control systems, PCS, are primarily used for electronically monitoring and controlling the manufacturing or industrial processes. In addition, PCSs are also used in conjunction with safety systems in detecting unsafe conditions and protecting humans and the environment. The figure below depicts a process control system that monitors and controls the pH level of a mixture through a sensor, an automatic controller, and a pressure-sensitive valve. The principal objective of process control is to maintain the controlled variable at a steady state or desired value. The process control mechanism is triggered by factors such as external disturbances, change in output specifications, change in input parameters, and varying process rates. The derivative control mode is used to address the issue of a sudden change or deviation of the controlled variable value from the set point value. This rate of change can be regarded as the error rate. The rate of response is proportional to the error rate in the controlled variable value. When the error rate is positive or increasing, the response rate increases as well to neutralize the increase in error rate. As the error rate starts to become stable up to the maximum level, the response rate slows down. The integral control mode is used to address the issue of constant difference between the set point value and the controlled variable value. This constant difference is referred to as the offset. Often occurs when the proportional mode, described below, is applied. The system applies an integral function to continuously add or subtract to the controller output until the offset ceases to exist. The onset control mode is used for processes wherein the controlled variable value changes at a very slow pace. This condition appears mostly in processes where temperature and/or pressure values are controlled. This control mode works on binary conditions, fully on or fully off. As the controlled variable value reaches the upper set value, the controller is turned on or off accordingly. Likewise, when it reaches the lower set value, the controller is turned on or off in response to the set condition. The proportional mode of control is used to respond to a controlled variable value that has deviated from the set point value. The magnitude of response is in direct proportion to the difference between the controlled variable value and the set point value, also called the error value.